So it turns out that there are a few rules that we have with our derivatives. So instead of just taking the derivative from scratch every time that we see a function, we are almost always wanting to find the derivative using our rules instead. And when I say our rules, I mean what I'm about to show us right now, right? So maybe we have two functions f of x plus g of x. And let's say we want to take the derivative with respect to x of both of these functions. Well, if things distribute the way we want them to, then in a perfect world, it would turn out d over this is equal to the derivative with respect to x of f plus derivative with respect to x of g. And even if the world isn't perfect, it turns out this at least is good enough because this is true. So our derivative, in a sense, distributes across addition. Well, luckily for us, it also distributes across subtraction. So if I maybe make this plus and minus look a little bit better, then the derivative of f plus or minus g is the derivative of x of f with respect to x plus or minus whatever that original operation was with the derivative of g. Well, it also turns out that if I have a constant times my function f, then that constant kind of just comes out front. I say it comes along for the ride, but it doesn't really do anything. So constants never really mess with our function. So if I have something like 2 times f of x, then when I take the derivative of it, this turns into 2 times the derivative of f. Okay? So sometimes it may simplify things to just pull any constant that we're multiplying by all the way out front. However, if the only function that I have, or if the only term that I have is a constant, that is always just going to be 0. So if I multiply by a constant, that constant comes along for the ride. But if I take the derivative of just a constant, then that just goes straight to 0. Then, if we add or subtract two functions together, maybe the next natural step is to multiply two functions together. So this is called our product rule. So it turns out the derivative of f times g is going to be this funny taking turns kind of thing. So what happened before with addition was you just took the derivative of each piece, right, and kind of kept the operation. That is not going to happen with multiplication or division. So with multiplication, it's going to be f prime times g plus f times g prime. So this is what I mean by saying you take turns with the derivative. The first function gets it first, and then the second one gets it next. So f prime of g plus f times g prime. And yeah, I did switch notation halfway through, right? Writing the prime instead of d over dx. But again, that's just different ways of writing the same thing. The derivative of x times g plus f times g of prime, the derivative of g. Okay. Well, like I said, whenever we have division, that also is not going to turn out as nice as addition or subtraction. And this is what we call the quotient rule, right? Because quotient is referring to a fraction. Some division, right? It's another name for division is quotient. Um, Now, this starts out a lot like the product rule. F prime times g, and then minus f times g prime. So far, all we've changed with the product rule is instead of an addition, we have a subtraction, except we also need to divide by something, right? We started with division, there's no way we can escape having some division somewhere, so it turns out this is equal to f prime times g of x minus f times g prime, all over g of x squared. And some people write this differently. Sometimes people will put the 2 like right here instead of like on the outside of the function. And that is different notation of writing the same thing. Uh, g squared of x is g of x squared. I prefer to write it the way that I wrote it down there, but it earnestly is the same thing. Okay, so these are the very generic function rules that we're going to keep quoting again and again and again for a lot of our functions. There is one more that comes in a little bit later of a section, but these are the basic ones that we're going to use for all kinds of functions. However, there is one more rule called the power rule. And that is when we have something that we want to take the derivative of. Now look, something like x to the n. Now, in class, I showed the proof of the power rule, and I got a lot of blank stares, so I'm not sure if y'all really want to see this again right now. I can, there's plenty of proofs online that you can find this for, and I don't want to waste your time in this video reminding us of the rules. So I'm just going to write out the result, and that is that power, whatever that number n is going to come out front and get multiplied by x to the n minus 1. And I wrote power rule all the way over here, but okay. So, if I want the derivative of x to the fourth, the power rule says that that is just going to be 4 times x to the 4 minus 1. Well, 4 minus 1 is just 3, right? So the power comes out front, and then we subtract 1 from the power. Very good. Now, sometimes we have powers that are not nice and clean numbers. So something like pi, right, is a little bit of a gross number, but we can still take this derivative so that exponent comes out front. We have pi times x to the pi minus 1, and it turns out there's not any nicer of a way to write pi minus 1. So we're going to do the same thing. Derivative with respect to x of x to the square root of 2. That square root of 2 is just going to come right out front, and there we're going to have square root of 2 minus 1 all in our exponent, right? That's all up top. So I can't write square root of 2 minus 1 any nicer than just square root of 2 minus 1. Same thing with pi, right? So most of the time it does simplify into something nicer, but technically we still can take this derivative even if it doesn't. Now the next, again, the power rule comes up a lot. The next trick is when we have something like the square root of x. Well, I have tried to show in class a few times that really any of our roots is actually an exponent. So I can always write a square root, a cube root, whatever kind of root as an exponent. So it turns out the square root is x to the 1/2 power. Well, now do the power rule on this. So the 1/2 comes out front. We have 1/2 minus 1 in the exponent, and we can simplify that. 1/2 minus 1 is negative 1/2. And it turns out this is a perfectly valid answer, right? This is 100% correct and a semi-reasonable place to stop, right? you will write, once you get into differential equations or something like that, um, this is a perfectly valid answer. However, for us, a lot of times it is useful to rewrite it so that we see it a little bit better. We understand it a little bit better. So having a negative exponent means we go upside down, right? We take this reciprocal. So this is 1 over x to the 1/2. But again, doing the 1/2 power is the square root. So, funnily enough, the derivative of the square root of x is 1/2 times 1 over the square root of x, which is really interesting, right? And it turns out that it's still the power rule. Um, and the same thing happens if it's like a cube root or a fourth root, right? Then we just write this as x to the 1/3 power and use the power rule on that thing, right? Okay. So these are all the basic examples of functions of the rules that we have with our functions. So let's do a couple of examples where we need to use these rules. Now, if I have, let's say, a really nice polynomial, 3x to the third minus 40x squared plus 2, right? And I take the derivative with respect to x of this function. Well, now, first things first, I would want to break this up into individual pieces. And it turns out this sum slash difference rule, right, adding or subtracting, I can just look at the derivative of the individual parts. So we typically aren't going to write this step, but I'm just writing this down to make it clear. We're going to take the derivative of each piece. And I wrote this part kind of weird, right? Um, oh, plus the derivative of this negative. Really, this minus sign can just kind of come out front, right? If we're adding by something we're subtracting, that's the same thing as just subtracting, right? Um, so we're just taking the derivative of each piece. Well, derivative of 2 is a constant, so that's 0. Derivative of 40x squared. Well, this 2, well, sorry, first, this 40 is going to come along for the ride, right? That's the constant rule, or the multiply a constant rule. Now the power rule says this 2 is going to come out front, and then we're going to have 2 minus 1 as our exponent. But we're subtracting this term still. Now derivative of 3x to the third. Again, this 3 is going to come out front, or sorry, come along for the ride. The 3 from the exponent is going to come out front. And then we're going to have x to the 3 minus 1 power. Now we can simplify this a little bit. 3 times 3 is 9. 3 minus 1 is 2. 40 times 2 is 80. 2 minus 1 is 1. But we don't even write the same way I'm not writing the plus 0, right? I oftentimes don't even write to the first power. So it turns out we're going to do 9x squared minus 80x, right? You can leave it to the first power. It doesn't make a difference. This is a perfectly fine step to stop at. You typically would want to simplify it, you know. Yeah, we didn't do anything crazy from the last step to this one, but you typically do want to simplify it, right? If you can do 3 times 3, do it. If you can do 3 minus 1, do it, right? So, very good. Now, the next example, I'm going to do something like this. 4x minus 1 times 2x plus 2. And let's say I want to take the derivative of this? Well, we have options, right? I can multiply these two things out. And it turns out, if I FOIL this, as we say, 4x times 2x is 8x squared. 4x times 2 is 8x. Negative 1 times 2x is negative 2x. Negative 1 times 2 is negative 2. So this should be the derivative of 8x squared plus 8x minus 2x is plus 6x, and then our minus 2. And now I break this across each term. Derivative of a constant is 0, so derivative of this negative 2 would be 0. Derivative of 6x, um, I realize I didn't write the rule out for this one because it kind of sits inside of the power rule. So we can do this with the power rule. So this is a 1 in the exponent. So we're going to multiply by 1, and then x to the 1 minus 1 power. And derivative of 8x squared, the 8 sticks out front. We're going to multiply by the 2, and then do 2 minus 1. Well, 2 times 8 is 16, and 2 minus 1 is 1. 6 times 1 is still 6, and 1 minus 1 is 0. So this is really x to the 0th power. Well, anything to the 0th power is just 1. So it turns out this is just 16x plus 6. Well, again, something else to note about this kind of derivative step is the derivative is the slope. Derivative is slope. So, derivative of a line should just be the slope of that line. So looking at 6x, that is a line that is linear, so that derivative should always be the slope. And that does work out. So we just did it using the power rule, but it turns out really in our head we shouldn't really be thinking of it as an instance of the power rule. You can, but it might be simpler in your head to just say this is linear, so what is the slope, right? So that's perfectly fine. However, the way that I immediately wrote this is as a product. So it should also be valid to use the product rule for this thing. So instead, let's do d dx 4x minus 1, right? Derivative of this thing times 2x plus 2 plus, the first part is normal, times the derivative of the second part, 2x plus 2. Now, I'm using brackets whenever I write the derivative, only to make it a bit more clear what I'm trying to take the derivative of. Um, yeah, technically you don't need to use brackets for this kind of thing, but I just am choosing to make it a little bit more clear, right? Um, so now the derivative of 4x minus 1, well, like I said, that is a line, and what is the slope of the line 4x minus 1? Well, that slope is just 4. Times, sorry, these need a parentheses there, 2x plus 2, right? The second term, plus 4x minus 1 times the derivative of the line, 2x plus 2. Well, what is the slope of that line? Just 2. So when I distribute 4 to both terms here, I get 8x plus 8. And then I distribute the 2 to both terms here, 8x minus 2. And now when I combine all of my terms, 8x plus 8x is 16x. 8 minus 2 is 6. So I end up with 16x plus 6, which exactly matches the one I got over there. So yeah, you can expand things out, but sometimes it's just easier to use the product rule. And by sometimes, I mean oftentimes. And also sometimes we genuinely just have to use the product rule. Now I could have done a very similar thing instead with the quotient rule. So let's say I had 4x minus 1 over 2x plus 2. And I want to take the derivative of this quotient. Well, now this isn't something that we really get to write any different, right? Because the product of two polynomials was a polynomial, but oh, the product of these two polynomials gave us just some other polynomial to take the derivative of, but down here, the derivative of a rational function we don't really get to write as a nice clean polynomial. So we do have to use the quotient rule. So that is f prime times g minus f times g prime all over g squared. So one way that people write it, they will call it top and bottom. And so they'll say um, d top bottom minus top d bottom over bottom squared. But I don't think, I don't know, that doesn't really connect with me. Maybe it connects with you, um, but it does not connect with me. I just have to write it out like that. Okay, so now the derivative of each piece, again, f of x in this case is 4x minus 1. G of x is 2x plus 2. So f prime of x is the derivative of f. Well, that is a line, so the derivative is a slope, so that's 4. G prime, the derivative of that line is its slope, so 2. So plug all of those pieces in to this form that we have, this formula. F prime is 4. G is 2x plus 2. Minus f is 4x minus 1. G prime is 2. And then all over g squared, so 2x plus 2 squared. And yeah, it does turn out we can simplify this, but oftentimes we kind of stop there, oftentimes. I'm going to go ahead and write the next line, or a couple more lines, I guess, just to be, you know, confident. So distributing the 4 to both parts gives us 4x plus, sorry, 4 times 2 is 8, so we get 8x plus 8. And then distributing the 2 and the minus sign to both of these terms, we're going to have negative 8x minus, sorry, negative times the negative gave us positive, so negative times the 4x gave us this negative 8x, negative times the negative 1 gives us plus, and then this 2 times 1 gives us 2. All of that over 2x plus 2, and I'm going to square that out. This is going to be 8x squared, sorry, 4x squared plus 8 plus 4. And then we can combine some terms. 8x minus 8x disappears. This is going to be 10 over 4x squared plus 8x plus 4. Okay, so again, there was no way of avoiding the quotient rule with that one. Very good. And it is my advice that you do write down each individual piece, right? I identified one part as the top and the other one as the bottom, and then I took their derivatives. So showing my work here is going to be so incredibly necessary, especially when these get a little messier. Um, like the formulas like this, right? Where plugging them in feels awkward sometimes. Okay, so very good. These are the basic formulas for taking derivatives. So now we're going to depart from only using the limit definition, and we're actually going to start using our rules to kind of take these shortcuts. Very good. Where is the mouse button?